Here I'm going to talk how we analyze or describe curvilinear motion using polar components. So what is a polar component? So polar coordinate system is this one. So instead of using an x or y, if you want to describe the position of any object here, we are going to use the distance from origin to that part, okay, using this radial direction and this theta, the angle from your reference line to the radial line, okay. And then we call the r direction is radial direction, and then once you set the radial direction, this is radial direction, and the orthogonal to or perpendicular to radial direction, this is called transverse direction, okay. Your particle is P is here, and then I want to locate P using your R and theta, okay. So that means this is my reference line, and then as I said, these are the radial direction. So this R is a radial direction, and then another line that perpendicular to this radial direction here, this is transverse direction, okay. So we just put the theta because this is the direction of the change of the theta, so we put the theta here. The radial direction is just called R, and at the same time, because we defined those two directions, so we can also think about the unit vector of my radial directions. So unit vector is UR, and the unit vector along the radial direction, transfer direction is U theta. As you imagine, if this particle changes position of over there, then obviously your UR and U theta will change of their direction, right? Because this is kind of keep moving, then the theta will change, R will change. So the direction, this position is different from here. So even though UR, U theta, the magnitude are the same as a 1, but the direction UR, U theta is keep changing. Before, when we use Cartesian coordinate system x and y, okay, that even though the particle is keep moving, our xi and ji, these are unit vector of these two reference, does not change. But in this polar coordinate system, the ur, u theta is keep changing depending on the motion, depending on the position of the object. So let's look at this one. This is a particle. This is a motion. So when this one is moved to, here, then as you see that this ur, u theta at first position has been changed because this is now ur and this is u theta. So direction is suddenly changed because your theta and r also changed. Okay. How we can get the velocity, describe or analyze velocity in polar coordinate system. Now look at this one. Your r, okay, so how do you define the r? So your r is time of function, right? R is equal to what? So r, so right now this is your particle and this is your r direction and this is distance r, but this distance r is keep changing as a function of time. So I'd like r is keep changing, but what's the direction? That is ur direction. That's it. So these are position. These are position vector. Okay, position vector. Then how about the velocity? So velocity is dr over dt, right? So now we have two terms here, so I want to do that. First I want to take dr over dt first, and ur, and plus r and dur dt. That means this dr over dt is time rate of change of the distance of this r, okay, and ur, and then r and time derivative of my unit vector of ur, okay. So what is this term? So before, when we use Cartesian coordinate system, di over dt and dy over dt goes to 0 because ij direction does not change. But this ur, okay, ur, even though the magnitude of ur is always the same as 1, but as this one is moved, the r direction is keep changing. That's why this one is not 0. So how do you define the dr over dt? Let me explain this one. So just imagine that this is our first position and this is our second position. So right now at the first position your r was here, and second position is r is getting longer, getting strengthened. So r, it became r prime, and also theta is changed. Okay, so in this one r dot prime is r prime minus r over delta time t. That's the r dot. But anyway, so I want to look at I just want you to look at this u theta is still kind of changed when this particle moved. Okay, so if you align these two u theta, the angle, into one like that, so I just align the center together here, and this is theta x. So this is the change of angle over time t, okay. And then since these are all the magnitude of vectors is 1, so these are all like all the same the length. So maybe I can make like a circle like that because everything is 1, but this is just rotating about this center. Then here, okay, because over the time the ur is changing, so I say ur prime minus ur is delta ur, okay. This is ur at a new position, this is ur at a before position, so the subtract is delta ur like that, okay, delta ur. And this one too, I think this one should be u theta dot, and this one is just u theta. So u theta dot minus u theta should be delta u theta, okay. Then what is this value, dur over dt? So did you remember that the definition of our differentiation is like limit delta t goes to 0, okay, and then this is ur prime minus ur over dt, right? So that means this is a limit delta ur dot and delta t. And then if you look at this one, dur dt, this is if the delta theta is very, very small, this length should be close to the length of this arc, okay. So what is the length of the arc, which is close to ur? So the magnitude of ur should be the radius, which is r, times delta theta. So that's why in here, limit and delta UR, okay, delta UR magnitude is same as delta theta. Then what is the direction of delta UR? If this is very small, then this delta UR direction, this direction is the same as the U theta direction, right? Because right now this is going this way and U theta direction is going this way. So if this is very small, then this direction is same. So my delta UR can be write down like magnitude of UR and U theta direction. See, this is only the direction and this is a magnitude and this is my vector. So I replace my delta UR is the magnitude of UR, which is delta theta over dt, and then U theta. What is this? This is the delta theta over dt. So that is the time rate of change of your angle. That is theta dot and U theta. So sometimes we call this is omega, which is angular velocity. So finally we got delta UR over dt is theta dot and U theta. While we work on this one, let me try to get du theta over dt. So what is du theta over dt? Let's try to get this one too. Then this one is limit delta t is going to 0, okay, and then this one is delta U theta over dt. And then what is delta U theta? Delta U theta is, we can say this is magnitude of delta U theta, and then this direction is the same as the opposite of UR, because now the delta UR is going this way, okay, but this delta U theta is going inside here. So this is in parallel, but the direction is opposite, right? This is going out, this is going in. So that's why this one should be negative UR. So we know that this characteristics like that. So we replace delta U theta using this one. But what is this magnitude delta U theta? This magnitude is the same as length of arc. If delta theta is very small, that means that is equal to radius of 1 and delta theta and minus UR, okay? So this one is delta theta over dt and minus UR. So that's why this one becomes negative delta dot and UR. Okay, then let's go back to here. So we figured out that delta DUR over dt is the same as dot theta dot and U theta, okay? So your velocity becomes del R dot UR and R theta dot U theta. So this is the new kind of formula, the velocity in polar coordinate system. So what does that mean? Just imagine that the circular motion. So this is a pivot point, and then there's a particle, and then this is kind of rotating at a speed of delta theta dot angular velocity, which is theta dot. Okay, so this is omega. Then in this example, this is a circular motion, so that's why the position of R, the length does not change. That means this R dot will be 0. Okay, So that's why the initial first term is 0. And then r theta dot. So that means the velocity is determined by r theta dot. So that means if you know the angular velocity, then you multiply your r from your rotating point to the object with your velocity, the angular velocity. That will be your velocity. So this is velocity. Which direction? U theta direction. So this is a U theta direction. So this is r theta dot U theta direction. So if this object kind of keep moving in here like that, then your velocity is again here. This is another U theta direction as well. And this is r direction, this is U theta direction. Okay, then let's a little bit go further. So how about the acceleration? So now we know that this is r dot u r theta dot u theta, okay? And then we know that the u r dot u r dot, which means u r dt, is theta dot u theta, right? And then also I show you that u theta dot, which is u theta over dt, is negative ur, right? Then let's get the acceleration. So acceleration is dv over dt, which means I need to take derivatives here. So which means here r2 dot ur plus r dot ur dot. Okay. Let me just write down here again. Plus r dot ur dot, and this is first term, plus the second one. So we have three terms. So this should be a little bit long. R dot theta dot u theta, r theta dot 2 dot, and u, then r theta dot u theta dot. Okay. Then we replace u r dot and u theta dot with this one. Okay. So let's a little bit long, but let's just do that. Okay. U r dot is theta dot u theta. Okay. And r dot theta dot u theta dot. This one should be r theta dot and minus theta dot ur. I'll rearrange everything. So if you just look at the ur, then this is r2 dot, we just take care of this one, and then this one, so this is negative r theta dot square, plus we have 2 of r dot theta dot, and then r 2 dot u theta. So these are our acceleration. These are radial components, and these are our transverse component. Simple example. As I said, we have a circular motion like that, and then particle just rotating about this point. Then if we know the omega and alpha, let's say omega is angular velocity, alpha is angular acceleration, then omega is theta dot and acceleration is 2 dot, right? Since this is the circular motion, the r does not change. That means this term and this term will be all 0. So in this case, the acceleration should be negative r alpha ur and plus r, not alpha, omega square, okay, and alpha u theta, right? So that means you have the acceleration of this term along the radial direction. So that means you have a negative. So when this one is kind of rotating, you have acceleration of this direction, which is r omega square. Okay. And also you have acceleration along this direction, which is transverse direction, which is alpha. And then I told you that we know that the velocity is r omega. Okay, so that's why in this r omega square can be written like, because r omega square is r omega square over r, so this is v square over r. So that's why the acceleration of this radial component is equal to v square over r. So if you know the velocity of the object, then you just divide by r. That becomes your acceleration component of your radial direction. Now, if you apply this one to the example, practice example, then everything will make sense to you more.